All right, welcome to chapter 5. Here we're going to be talking about thermodynamics throughout this chapter, which is basically just like the transfer of heat during chemical reactions. So first off, we're going to talk a little bit about the energy basics behind this, just so we can get an idea of what we're talking about, and then we're going to expand upon that the rest of the way, of course. So energy is the capacity to supply heat or to do work during a chemical reaction. And so here we're going to focus upon the heat part of it, as I think that the work part of it is a little bit more for the physics-based classes. Both super important, and like they really do tie together, but we're going to focus most of our time and energy in here into the heat. Okay, so heat is always transferred from the warmer object into the colder object. So if you ever think about this, like if you take a piece of ice and you put it into your hand and your hand starts to feel cold, what's really happening there is that the heat is being transferred from your hand into the piece of ice to melt it, because it's always going from the warmer object, your hand, into the colder object, which is that piece of ice. All right, so when we have chemical reactions, we describe them by the transfer of heat, and we describe them as either being exothermic or endothermic. And so exothermic is where heat is released into the surroundings. It's given a negative sign, and so exothermic heat exits the system, right? And so I like to think about that as the fact that both those words start with EX. And then endothermic is where heat enters the system. En is endothermic, right? En there as well. So again, right, we have a negative sign for exothermic and a positive sign for endothermic. We'll get a little bit more into why we have those signs here in a little bit. All right, units of heat. So a lot of times you might want to think about heat being the same thing as like temperature, but it's not. Okay, temperature has units of things like degrees Fahrenheit, degrees Celsius, and Kelvin. So we saw earlier how to like convert between those units and stuff like that. But heat is not temperature. Heat has totally different units. Heat has units of calories, which is like a lowercase calories there, and uppercase calories, which are also kilocalories. And so I bet we can figure out that 1 kilocalorie is equal to 1,000 calories. Okay, we probably heard this term calories before, right? If you look at some food or something like that, right, and you ingest a certain number of calories, the calories in food are kilocalories, all right? You may also stumble across like heat as units being in joules. Joules are the SI unit for heat, and they're the ones that we'll use in chemistry for most of the things, although we might be doing a lot with calories as well. So just get used to the fact that they have different units in temperature because they are different things than temperature is. Our next little topic here is something that we're going to call specific heat capacity. All right, and that is given the symbol of a lowercase c there. And that is the amount of heat that it takes to raise the temperature of a substance by either 1 degree Celsius or 1 Kelvin. Basically, right, since the Kelvin and Celsius scale both go up by the same amounts, those are the same thing. And this is very specific upon the substance itself. I do want to point out, like water has a high specific heat capacity. Okay, well that means that it takes a lot of energy, right? A lot of heat to raise the temperature of water. Right? Think about putting a pot of water onto a stove and trying to heat it up. Right? It takes a long time. Right? They always say like a watch pot never boils, and that's because of that. Whereas if you look at things like, say aluminum there, right? Aluminum has a specific heat capacity of 0.897. That's a very low number in comparison. Think about putting like an aluminum pan onto the stove and turning the stove on, right? It does not take very hot for that pan to heat up. That's because of its low specific heat capacity. Right, I also want to notice that the specific heat there for water is 4.184 joules per grams degrees Celsius. So I want to point out that 1 calorie is equal to 4.184 joules. So the specific heat for water in calories is also 1 calorie per grams times degrees Celsius there. Right? Kind of like a little interesting thing, because one thing's equal to each other, we can do that with another thing. Those are equal to each other as well. Okay, so we're going to calculate the heat of something. All right, and so in order to calculate the heat of something, we can do that by the following equation, where heat is given the symbol of Q. All right, and Q is equal to M. M is mass times C. C is the specific heat capacity times delta T. All right, and delta T is going to be the final temperature minus the initial temperature. And I want to point out that anytime that we have a change in something, we always do final minus initial. All right, so keep that in mind as you kind of solve things throughout the rest of the semester. It's always final minus initial. So here we're going to place a beaker of water, all right, which is 50 milliliters, on a hot plate and raise its temperature from 20 to 47 degrees Celsius. How much heat was absorbed? All right, so we needed to absorb heat because the temperature went up in this case. So while temperature and heat are not the same thing, they are interrelated via this equation, as you notice. Okay, so number one, we're going to calculate our Q. It is equal to our mass of our water. Okay, well, water has a density of 1 gram per milliliter. So 50 milliliters times 1 gram per milliliter is 50 grams. So we've got 50 grams. All right, times our specific heat for water. If we went back to that previous table, it is 4.184 joules per grams times degrees Celsius. All right, times our change in temperature. So T final, and this is a rare case where we can use Celsius, so let's just go for it, because a lot of times as we go forward, we're going to be doing a lot in Kelvin. But here, we're cool to just stick with Celsius. So 47 minus our 20 degrees Celsius in there. All right, so if we notice here, like, we're going to have our Celsiuses are going to cancel, our grams are going to cancel, and we're going to be left with units of joules in here. Okay, so, and joules are, of course, a unit of heat. And so when I calculate this out, I get an answer of 5.65 times 10 to the third joules. All right, notice that there's a positive sign on here. All right, that means that heat entered. Right, remember, that meant that this was an endothermic reaction. So next we're going to turn our attention to something that we call calorimetry, which is basically how we can calculate this heat transfer. So we're going to be doing, like, experimentally, and we're going to actually do this in the lab as well. So calorimetry allows us to look at a reaction and see whether heat is either absorbed by that reaction or if it's given off during the reaction. So over there on the left-hand side, like, I have a system in which is an exothermic process, and so heat is given off into the surroundings. And when heat is given off into the surroundings, we will see that as an overall temperature increase during that, right? And so on the right-hand side there, right? That is where we have an endothermic process. And so what we have is that the heat is going from the surroundings into our system. And when they go from the surroundings into our system, then heat is absorbed, it's entering the system, and the temperature that we're going to see that as the temperature of our solution surrounding is going to decrease over time. All right, so there are two types of calorimeters, and the one that we're going to be dealing with is what we call a coffee cup calorimeter. It is a really fancy piece of equipment here in which we have two coffee cups or two styrofoam cups nestled inside of each other, as seen in our little picture here. And then what we can have is we can let the reaction take place inside of there. All right, and so the reaction takes place in here. And when that reaction takes place, then heat is either given off into the surroundings or heat is needed to go into the reaction itself in order for it to take place. One of the two things has to happen, and so we'll see that as a temperature change. All right, and so again, right, if we see the temperature go up, it is exothermic. If we see the temperature go down, it is endothermic. Right, so this is a really neat way of using temperature in order for us to look at a change in our heat by having a reaction take place in a closed vessel. Okay, now we can also use what we call commercial calorimeters, which are usually what we call a bomb calorimeter, in which case they are really sophisticated. They've got like a really tight-knit little bomb area in which the reaction can take place. Gives off much less partial or parts for error that they could occur and stuff like that. But you know what? For our purposes, like a coffee cup calorimeter just gets us through what we need to understand what's happening for calorimetry. And so we're going to see then the principles of that and then work an example problem here coming up shortly. Okay, so as we've seen, since calorimetry is an exchange between the substance and the surroundings, right, what we can see there is that heat, right, is going to go either into the substance from the surroundings or vice versa, right? And so what that means is that the heat has to go somewhere. And so the heat, or our Q, for the reaction has to equal, all right, the same magnitude of heat for the surroundings, but they're going to have opposite signs of each other. Okay, now this isn't really telling us which one is, having heat enter it or exit it yet. We can solve for that in a little bit, but they just have to have the exact same magnitude or the exact same sign, or not sign, sorry, the exact same size of their values, but the signs are opposite from each other. So another way of saying this is because Q is equal to MC delta T, right? I can say that MC delta T, right, for the reaction is going to be equal to negative MC delta T for the surroundings. All right, and that is going to allow us to make calculations here for these calorimetry type problems. Almost all of them are going to be set up this exact same way, where either we're going to calculate just straight up the heat of something, or if we've got a calorimetry problem, we're going to set it up just like this, where we write those equations and set them equal to each other. Just don't forget that, right? Negative sign that's in there. So let's find ourselves solving a calorimetry example here. So it says, how much will the temperature of a cup of coffee, all right, so we're given our cup of coffee is 180 grams. All right, we got our cup of coffee at 95 degrees Celsius. How much will it be reduced if we place a spoon, right, 45-gram spoon with its specific heat there at 25 degrees Celsius? We're going to allow them to reach the same temperature, reach a temperature equilibrium. All right, so we're going to assume our coffee has the same density as water. So density is 1.00 grams per milliliter, and our specific heat is 4.184 joules per grams times degrees Celsius there. So we're assuming those two things from that. Okay, so what we have here is we have the Q for one of our things. All right, now not really a reaction taking place, but we've got the Q for a coffee, say, is equal to the negative Q for our, say, spoon. Okay, they're going to be equal to each other in magnitude there, but opposite in sign. So again, right, that is MC delta T is equal to negative MC delta T. So I'm going to just call the coffee my left-hand side. So I've got 180 grams of my coffee times its specific heat, which we said is 4.184 joules per grams times degrees Celsius. And our change in temperature. Okay, so T final. Well, wait a minute. I'm kind of looking for the final temperature, so I don't know that yet. Okay, minus our initial temperature. Well, the initial temperature of the coffee was 95 degrees Celsius. All right, that is equal to negative. Okay, for the coffee, or for the spoon, 45 grams. That's how much it weighs. Right? That's its mass. Its specific heat is given to us as 0.24 joules per grams degrees Celsius. Okay, now again, right? I don't have this final temperature of the spoon yet. We're really kind of looking for that, right? So T final in there, and then the initial temperature is 25 degrees Celsius there. Okay, so I'm going to kind of work through this and, do this algebraically here. So I've got my 180 times my 4.184 is I've got 753.12. All right, and so we're going to take that times T final minus, and we're going to take that same number times 95. So I get 71,546.4. Okay, that's equal to my other side. So I'm going to do, negative, all right, remember 45 times 0.24, which is 10.8. And then I've got a negative 45, and that's T final, times T final. All right, I've got negative 45 times 0.24 times a negative 25 is positive 270. All right, so I'm going to get my T finals together and my non-T finals together. And so I get 71816.4 is 763.92 T final. So my T final is 94.01. Or this dropped by 1 degree Celsius, and that's it. All right, so when we put that spoon in, it changed the temperature a very small amount, but that's all that it changed it. All right, next we're going to be like figuring out enthalpies. All right, so enthalpy is where we're going to be solving for basically the exact same thing as heat, but it has to be at constant pressure for these equations to work. And so good news is that whenever you're working in a lab or something like that, right, I mean, the odds of the pressure changing very much in the lab are very small. And so we can usually assume that we're at constant pressure, which makes these great to just work directly with enthalpy as our source for heat calculations. Okay, so we can directly calculate the enthalpy of something because the only way to really work with enthalpy is if there's a change to a system, right? It's just like, because I said that, we're basically calculating the heat, and really heat is a measurement of, a transfer of energy. And so you can't really calculate enthalpy if there's not like a transfer of that energy somewhere along the way. And so we really have to calculate an enthalpy change. All right, now again, we are going to be calculating these at a constant pressure because, we were going to be working with things in a lab where, we're in an open space, in an open environment where the pressure really isn't going to change. And so once we do that, right, we can calculate these enthalpy changes. Now I want to notice something very important on this slide here is that notice that our oxygen in this case has a coefficient of 1/2. And we have learned that we can't have coefficients of 1/2 in balanced equations. This is not a balanced chemical equation. Okay, this is an enthalpy equation. This is the enthalpy of formation equation. And when we calculate our enthalpies of formation, what I'm doing here is that this is showing us forming 1 mole of water. And when we do these, right, when we have formations, are always for 1 mole. Right? And so in order for it to technically balance out, the oxygen has to be 1/2 there. Now, again, it doesn't work for a chemical equation, but for an enthalpy of formation, that's why we've got that 1/2 of an oxygen that's in there. So all of our enthalpies of formation here are going to be forming 1 mole of whatever we're interested in. And all of these can be found in a table, right? And so usually you'll look them up in some sort of a table somewhere along the lines. If you're using an OpenStax textbook, like our textbook is in this class, right? That is in Appendix G, you'll find a table of formation constants, and those are all of these things where you're forming 1 mole of all these different species. So now we're going to talk about the conventions for thermochemical equations. And there are several of these conventions that we're going to be interested in. All right, number one is the super obvious one that we've already talked about, whether something is exothermic or endothermic. It says that delta H is less than 0 if it's exothermic. That is the same thing as saying that we have a negative delta H. If it is greater than 0, it is a positive delta H. That is implying that we have an endothermic reaction, the way that it's written. Now, the next statement says that if we have a process that's exothermic in one direction, it is endothermic in the opposite direction. Okay, so on our previous slide, we saw that hydrogen plus 1/2 an oxygen producing liquid water had an enthalpy change of negative 286 kilojoules. All right, so that is an exothermic reaction, right? Now look at the next equation that I've got written there. All I've done is I've taken that equation and I've flipped it around. So the reverse reaction, liquid water decomposing into hydrogen gas and 1/2 of an oxygen. Okay, look, that has the exact same value for our enthalpy change, but note the change in sign. So when you reverse a reaction, right, the value for the enthalpy is the same, but you are changing whether it is exothermic or endothermic. Okay, so the top reaction is giving off heat when that reaction takes place. For the reverse of it to happen, heat needs to enter the system for that to happen. Right now, also notice that it depends on the state of the material. So, right, we're going back to our initial one there, right, that we've got our hydrogen and our 1/2 of an oxygen producing 1 mole of our water liquid, right? And we have an enthalpy change there of negative 286 kilojoules, right? That is for the formation of 1 mole of liquid water. The formation of 1 mole of gaseous vapor water is different than that for liquid. So we need to pay attention to the states of matter when we start calculating problems using these. And we are going to be looking these up in tables and using them to calculate problems. So pay attention to the states that they're in order to get the right values. Because for gaseous, notice that it is a negative 242 kilojoules. That's a different value. And we need to make sure that that is different and that's accounted for. The standard enthalpy of formation for things is basically just breaking them down into their elemental parts and then combining them to form 1 mole of whatever we are interested in. So if we think back to our previous example there, right, where we were forming our 1 mole of, say, liquid water, right? And we had a half a mole of oxygen and 1 mole of our hydrogen in order to produce that. Right, so we're just working backwards in order to get something. So if I wanted to, say, form here this magnesium carbonate, right? I've got my magnesium carbonate like so, right? All we're going to do is on our reactant side is that we're going to break this down into the individual elements. So I've got some magnesium, I've got some carbon, and I've got some oxygen, right? All of them in their elemental forms. Okay, well, now let's pay attention to the fact that we have 1 magnesium, right, and 1 magnesium, 1 carbon, and 1 carbon. But I've got 3 oxygens there, and I've got, oh, that O2 over there. So here's a case, again, where we can use a fraction in order to get that, right? So 3/2 of an oxygen, right? 3 times 2 is 6, divided by 2 is 3. That gets us the right number of those oxygens there. So that's how we're going to break these down in order for us to write out a balanced standard enthalpy of formation reaction. Right? And we're going to use these soon in order for us to calculate the overall enthalpy changes. Right? In order for us to calculate the enthalpy changes, we're going to use the enthalpies of formations in order for us to get there. And to do this, what we're going to do is we're going to be calculating the standard enthalpy change for the individual formations, and we're going to do the sums. If we remember, that is what these sigmas stand for, right? The sum of what follows it. That means we're going to add together everything that follows it. So we're going to do the sum of, all right, the number of moles that we find present times the enthalpy of formation of the products, and then we're going to subtract off the sum of the reactants. We always do products minus reactants. Right? There's going to be one case where we don't do products minus reactants. That's at the very end of this chapter. But every other calculation that we do in Chem 1, Chem 2, like all of your Chem Lives, you're always going to work with products minus reactants on things. Okay, so again, right, our sigma is the sum of n's are the stoichiometric coefficients that are out in front. So they're found from our balanced equation. And then the enthalpies of formations are table values that have been calculated by running experiments in a lab. Okay, so let's look at an example doing standard enthalpies. Okay, so what is the standard enthalpy change for this reaction here, where I've got some glucose plus some oxygen producing carbon dioxides and water, some liquid water there. Okay, so in order for us to calculate this, right, what we want to do is we want to look up their values, and we're going to plug those values into our products minus reactants. Okay, so we're going to do products minus reactants. Okay, so our delta H is, so what I'm going to do is I'm going to start with one of my products here, right? And I'm going to go ahead and go with my carbon dioxide there. So I have the coefficient out in front of 6. So I'm going to put that in. So I've got my 6 moles of carbon dioxide, all right, times the value that I look up for carbon dioxide, and we got to make sure that it's in the gaseous form, is negative 393.51 joules per mole. All right, to that we're going to add, because we're taking the sum of all of our products, so we're going to add to that our 6 moles of water, liquid water. So we look up our liquid water, and remember that our liquid water is negative 285.83 joules per mole. All right, next off, we're going to take all of that and we're going to subtract off our reactants. So I have 1 mole of our C6H12O6 solid, and it weighs negative 1273.3 joules per mole. And we're going to add to that. All right, we have 6 moles of oxygen, and oxygen happens to be 0. All right, little piece of information. All elements, the standard enthalpy of formation for all elements are 0. So we didn't have to look it up, although it's good practice to go ahead and do it if you don't remember that. So, but you know, they are all 0, just like oxygen in its elemental form, O2 is a 0 there. All right, now we're going to calculate then our enthalpy change by calculating everything through here, and I get this to be negative 2802.74 joules. Okay, now, a lot of times we want to write these as something that we call a thermochemical equation. All that is writing the equation, right, with all the states of matter and everything else here. And we're going to include in that, at the very end, the enthalpy change. That's the only difference than a balanced chemical equation, is that we're including that one little bit of information there. Right? So we can write that whole thing out. Okay, the last little bit of information here for this chapter is something that we call molar bond energies. Okay, now it takes energy in order to break up a chemical bond, because they're bonded together, they're held together, they're happy. In order to break that, you've got to like cleave that bond, you've got to put energy in to break them apart. So if it takes energy to break a bond, it makes sense that you actually gain energy whenever a chemical bond is formed. Okay, you can look up molar bond energies because, well, we have done this and we've figured out how much energy it takes to break apart a bond, and then they're going to be the opposite sign. But the same magnitude whenever you make a chemical bond. All right, and so we can look these values up and we can then make calculations doing them. All right, and when we do these, this is the only time, like I said, we're going to do reactants minus products. All right, it's always products minus reactants except for when we're dealing with molar bond energies. So just keep that in mind as you're working through them. Don't get confused on it. So let's do an example here. I've got some molar bond energies over there in a table for us to kind of work with. All right, and we want to calculate the delta H, I don't know why that's not there, I missed a delta, for the following using molar bond enthalpies. So we've got our methane plus 2 oxygens forming carbon dioxide and 2 waters. So what I like to do here is I like to draw everything out. Okay, and so we're not really to the point where we have drawn out and been able to do the shapes and everything for all our molecules. That's coming in chapters 7 and 8. But we can always look these up if we need to work them out. So what this looks like is we've got, for our methane, it looks like this. For oxygen, okay, an oxygen is an oxygen double bonded to another oxygen. And notice that there's 2 of them. So there's actually 2 of those. All right, this is then carbon dioxide, which looks like that there. And then I've got 2 waters. Okay, so, right, when I want to calculate this out, right, what I'm going to do, right, are reactants minus products. Right, backwards from what we did before. Okay, so notice that there are 1, 2, 3, 4 carbon to hydrogen bonds there. So there are 4 carbon to hydrogen bonds, right? And so we look over there in the table, right? And we're given an enthalpy of 413 kilojoules per mole. So I'm going to multiply the 4 times 413 kilojoules per mole. Then we're going to add to that. There are 2 oxygen-oxygen double bonds, right? And they each are 495 kilojoules per mole. All right, so we're going to take all of that, which is 2642 kilojoules. Okay, we're going to subtract off our products. So we have 2 carbon double bond carbon bonds there. Carbon double bonded to oxygen bonds there, sorry. Times 799 kilojoules per mole. And then we're going to add to that. Okay, so again, there are 1, 2, 3, 4 hydrogen to oxygen single bonds. So we have 4 hydrogen to oxygen single bonds, which are 463 kilojoules per mole. Okay, so that side, right, our product side is negative 3450 kilojoules. Okay, so our answer then is going to be negative 808 kilojoules. All right, so that's how we calculate a molar bond energy example, and you will be doing basically the same. All right, we've finished another chapter. Chapter 5 in the books. We'll see you back for chapter 6.